Flying from London to New York in just 3.5 hours might sound impossible, yet the Concorde has regularly achieved this feat for nearly 3 decades. The engineering of the Concorde represents one of aviation's greatest technological achievements. This supersonic passenger aircraft pushed the boundaries of aerospace design, materials science, and propulsion systems beyond what many thought possible. Every aspect of the Concorde showcased revolutionary engineering solutions, from its distinctive delta wing design to its sophisticated engine management systems. Despite its eventual retirement in 2003, the Concorde's legacy continues to influence modern aviation. This video examines the remarkable engineering features that made supersonic passenger travel possible, explores why the Concorde stopped flying, and analyzes the complex technical challenges that its designers overcame. Through this exploration, you will understand why the Concorde remains unmatched in commercial aviation history. The revolutionary design philosophy. The Concorde's design philosophy represented a remarkable fusion of aerodynamic innovation and materials engineering. At its heart was the distinctive ogival delta wing, which required over 5,000 hours of wind tunnel testing to perfect its shape. This wing configuration wasn't just about aesthetics, it solved one of aviation's fundamental challenges, maintaining efficient lift at both subsonic and supersonic speeds. The aircraft's materials selection demonstrated exceptional engineering foresight. The primary structure utilized hydromanium RR58, an advanced aluminum alloy containing precise percentages of copper 2.5%, magnesium 1.0%, and nickel 1.2%. This specialized material provided the perfect balance of strength and weight, crucial for supersonic flight operations. Heat management posed a significant engineering challenge. During flight, the Concorde's skin temperature varied dramatically, reaching 261 degrees at the nose and 196 degrees at the tail. To combat these extreme temperatures, engineers developed a highly reflective white paint coating that offered twice the reflectivity of standard aircraft paint. The airframe's thermal expansion was so significant that the aircraft would stretch by 7 inches during flight. The fuel system exemplified innovative problem-solving. Engineers had to address unique challenges. One of the foremost issues was the need to effectively manage fuel under extreme conditions, including high temperatures and low ambient pressures encountered during flight. At high altitudes, the risk of fuel boiling posed a significant problem, requiring the development of advanced methods to maintain fuel stability and performance. Additionally, the system had to incorporate a sophisticated mechanism to utilize the fuel as a heat sink, enabling it to absorb and dissipate heat generated by various aircraft systems. The Olympus 593 engines, developed through a collaboration between Rolls-Royce and Snecma, delivered 17 tons of thrust each. These power plants represented a significant leap in propulsion technology, enabling sustained supersonic flight while managing the complex thermal and pressure conditions at high altitudes. The structural design incorporated numerous innovative features to handle supersonic stresses. The wing utilized sculpture milling, starting with solid metal pieces rather than traditional bolting and riveting. This technique enhanced structural integrity while minimizing weight. The fuselage design featured a narrow body allowing for abreast seating, complemented by the droop nose for enhanced landing visibility. These engineering solutions weren't just theoretical achievements. They enabled the Concorde to operate safely and reliably at its cruise speed of Mach 2.04, while carrying up to 128 passengers. The combination of advanced aerodynamics, materials science and propulsion systems made the Concorde a testament to human engineering ingenuity. Breaking the sound barrier. Supersonic flight presented unprecedented engineering challenges that pushed the boundaries of aviation technology. At speeds above Mach 1, aircraft face extreme pressures, temperatures, and aerodynamic forces that conventional designs simply cannot handle. The primary challenge of supersonic flight was managing the intense heat generated at high speeds. The Concorde inlet air temperatures exceeded 120 degrees during Mach 2 cruise, requiring specialized materials like titanium for compressor components and mnemonic 90 nickel alloy for the final stages. The overall pressure ratio at Mach 2.0 cruise reached a remarkable 82:1, with 7.3:1 from the intake and 1.3:1 from the engine compressors. The Olympus 593 engine represented a masterpiece of engineering innovation, achieving several groundbreaking features. Among its most impressive feats was its exceptional overall efficiency, reaching 43% during supersonic cruise. This efficiency was unprecedented, marking the highest ever recorded for any thermodynamic machine at the time. The engine's thrust distribution further highlighted its advanced design. It achieved a complex balance of forces, with 8% of the total thrust directly contributed by the engine core, 63% generated by the compression of air within the intake system, and an additional 28% produced by the pressure within the exhaust nozzle. This precise allocation of thrust sources demonstrated the engine's sophisticated aerodynamic and thermodynamic integration, ensuring optimal performance under demanding conditions. Equally noteworthy was the engine's exceptional durability and longevity. The Olympus 593 was engineered to endure an impressive design life of 25,000 operational hours for its major components. Moreover, critical elements such as the compressor and turbine blades were built to last up to 10,000 hours, reflecting meticulous attention to materials and structural resilience. During the cruise at Mach 2.02, each engine produced approximately 10,000 leaf of thrust, equivalent to 36,000 HP. The engine utilized partial reheat, providing a 20% thrust increase specifically for takeoff and transonic acceleration between Mach 0.95 and Mach 1.7. The sonic boom challenge proved to be one of the most significant barriers to widespread supersonic flight. The FIA banned civilian supersonic travel over land in 1973, limiting the Concorde primarily to transoceanic routes. The sonic boom's intensity was measured at 105 perceived decibel level, far above the 75 perceived decibel level threshold considered acceptable for unrestricted supersonic flight. Modern research focuses on reducing sonic boom intensity through innovative design approaches. NASA's X-59 experimental aircraft aims to keep shock waves separated from the tip of the nose to the end of the tail. This design strategy attempts to transform the traditional sonic boom into a softer thump comparable to a car door closing. The engineering solutions implemented in the Concorde's variable geometry intake system achieved remarkable pressure recovery, delivering an intake pressure ratio of 7.3:1 at Mach 2 cruise. This sophisticated system managed multiple shock waves to optimize engine performance while minimizing drag and fuel consumption. Technical marvels of the Concorde. Among the most sophisticated aspects of the Concorde's engineering were its advanced control systems, innovative fuel management, and groundbreaking navigation technology. These systems worked in harmony to enable safe supersonic flight. The Concorde pioneered the use of an analog fly-by-wire flight control system, making it the first commercial aircraft to employ this technology. The system was jointly developed by Elliott Automation Limited and Sphena, featuring dual autopilots with comprehensive control capabilities. This sophisticated setup allowed for hands-off control from takeoff through landing, managed through controls positioned on the glare shield for easy access by both pilots. The Concorde's fuel system was a marvel of multifunctional engineering, meticulously designed to perform three essential and interconnected roles. First and foremost, it ensured a reliable supply of fuel to the aircraft's powerful Olympus 593 engines, enabling sustained performance during both subsonic and supersonic flight. This function was critical to maintaining the Concorde's ability to cruise at Mach 2 speeds with precision and efficiency. In addition to powering the engines, the fuel system played a pivotal role in controlling the aircraft's center of gravity. By strategically transferring fuel between tanks located throughout the fuselage, the system allowed for dynamic adjustments to balance the aircraft, particularly during supersonic flight, where aerodynamic forces and fuel consumption patterns constantly shifted. This innovative approach eliminated the need for conventional trimming surfaces, reducing drag and enhancing fuel efficiency. Finally, the fuel system doubled as a sophisticated heat management solution. The fuel itself served as a heat sink, absorbing and dissipating excess heat generated by the aircraft's structure and onboard systems. This was especially crucial at supersonic speeds, where air friction caused the aircraft's skin to reach temperatures as high as 127 degrees Celsius. The aircraft featured 13 integral fuel tanks, arranged in 3 distinct groups: left main transfer, right main transfer, and trim transfer. During supersonic flight, approximately 20 tons of fuel would be moved between tanks to maintain optimal balance, compensating for a 6-foot shift in the center of the lift. This precise fuel management was crucial for maintaining stability at various speeds. The Concorde's navigation suite represented the pinnacle of 1970s aviation technology, incorporating triple inertial systems, dual Voordeem systems, dual ILS capabilities, dual ADF systems. The aircraft's avionics system was particularly notable for being the first commercial application of hybrid circuits. The air data computer automatically monitored and transmitted critical aerodynamic measurements, including total pressure, static pressure, angle of attack, and side slip data. The flight deck featured duplicated instruments on both the pilot and co-pilot sides, with separate systems supplying information to each set of instruments for redundancy. This redundancy was crucial for maintaining safety during high-speed flight operations. When the traffic collision avoidance system was later integrated, it necessitated a careful reorganization of the cockpit layout to accommodate the new technology while maintaining operational efficiency. The integration of these advanced systems made the Concorde one of the most technically sophisticated aircraft of its era. Its automatic flight control system could handle everything from turbulence management to fog landings, demonstrating remarkable capability and reliability. The comprehensive nature of these systems led some to question the need for pilots, though human oversight remained essential for safe operation. Engineering solutions for passenger comfort. Passenger comfort at supersonic speeds demanded extraordinary engineering solutions, particularly when flying at altitudes of 60,000 feet. The Concorde's sophisticated systems ensured a comfortable journey despite the extreme operating conditions. The Concorde maintained cabin pressure equivalent to 5,000–6,000 feet altitude, compared to 8,000 feet in conventional aircraft. This lower cabin altitude significantly enhanced passenger comfort during the 3-hour transatlantic flights. The pressurization system consisted of 4 independent air conditioning groups, providing redundancy and ensuring a consistent cabin environment. The key components of each air conditioning group included primary and secondary cooling systems, air and fuel heat exchanger cooling systems, water separator with ice sensor transducer, and distribution system with isolation valves. The aircraft employed multiple strategies to manage noise levels in the cabin. The distribution chamber collected air from all groups, ensuring continuous operation even if one group failed. Cabin isolation valves automatically closed during duct overheating events, preventing hot air from entering the passenger compartment. Temperature management aboard the Concorde was achieved through an advanced and highly efficient zonal system designed to ensure passenger comfort and optimal operation of critical systems. This system was divided into specific zones, each tasked with regulating a distinct area of the aircraft. The first group focused on controlling the temperature of the flight deck, providing the crew with a stable and comfortable environment. The second group managed the forward cabin, while the third and fourth groups were dedicated to maintaining appropriate temperatures in the rear cabin. The system incorporated multiple safety features, including overheat protection that activated at 210 to shore. The fuel heat exchanger had an automatic control valve that opened at 95 degrees, while the pneumatic temperature sensor limited airflow to 19 pounds per minute when downstream temperatures reached 205 degrees. Equipment bay cooling utilized a dedicated system of fans that extracted air from the cabin and forward electronic racks. This air was then exhausted through the forward discharge valve, maintaining optimal operating temperatures for critical systems. The main landing gear bay and flying control chassis bay received ventilation using conditioned air from the cabin underfloor area. This comprehensive approach to temperature control ensured both passenger comfort and the proper functioning of critical aircraft systems throughout the flight envelope. Maintenance and engineering challenges. Maintaining the world's only supersonic passenger aircraft demanded extraordinary resources and expertise. The Concorde required 57 hours of maintenance for every hour of flight, making it one of the most maintenance-intensive commercial aircraft ever operated. The Concorde's maintenance program was a meticulously structured and intensive process, reflecting the aircraft's technological complexity and unique operational demands. This program adhered to a rigorous hierarchy of scheduled checks, beginning with pre-flight inspections conducted before every departure. These were complemented by daily checks performed every 24 hours to ensure the aircraft's immediate readiness. More extensive inspections were carried out at regular intervals, including Check A after every 210 flight hours, Check B at 420 hours, Check C at 1,680 hours, and Check Illinois at 6,000 flight hours. The most comprehensive overhaul, Check D, was conducted every 12,000 flight hours, involving a complete disassembly and inspection of the aircraft to maintain its integrity and performance. The Olympus 593-610 engines, integral to the Concorde's supersonic capabilities, required specialized maintenance protocols. 5 critical checks were key to their upkeep. The spectrographic oil analysis program, conducted every 50 flying hours to detect trace metal contaminants. Analysis of magnetic chip detectors to monitor engine wear. Continuous monitoring of exhaust gas temperatures to identify performance anomalies. Oil consumption tracking to detect early signs of engine degradation. And regular borescope inspections to visually assess internal components for wear and damage. The manufacturing of spare parts for the Concorde posed significant challenges due to the aircraft's reliance on specialized materials and advanced construction methods. Precision was paramount, achieved through the use of numerically controlled machine tools for crafting parts to exact specifications. Electron beam welding techniques were employed for critical components requiring high-strength bonds, and the fuel tanks utilized specialized sealing process involving Viton material to ensure durability under extreme conditions. Maintenance costs for the Concorde were substantial, accounting for approximately 50% of its operational expenditures, a stark contrast to the 10% typical for conventional aircraft. By 2003, British Airways projected annual maintenance costs for their Concorde fleet to reach £40 million, highlighting the financial burden of sustaining the aircraft's advanced capabilities. The technical demands of the Concorde necessitated extensive training programs for maintenance personnel. Engineers required expertise in handling advanced materials such as titanium and high-duty alloys, maintaining complex electronic systems, and understanding the principles of supersonic aerodynamics. Specialized diagnostic procedures were essential for identifying and addressing potential issues, and maintenance teams underwent continuous training to keep pace with this aircraft's requirements. This included regular certification updates, training in the use of specialized tools and equipment, and operation of advanced diagnostic systems. Engineers were also prepared for emergency procedures and trained to monitor structural integrity with a focus on detecting material fatigue, thermal stress effects, structural degradation, and component reliability concerns. This comprehensive maintenance regime ensured the Concorde's safety and reliability, but also underscored the challenges of operating such an advanced aircraft. The interplay of specialized maintenance protocols, complex spare parts manufacturing, and intensive engineering training created a support infrastructure unlike any other, distinguishing the Concorde as a remarkable but demanding icon of aviation. Performance metrics and capabilities. The remarkable performance metrics of the Concorde set standards that remain unmatched in commercial aviation. Its engineering achievements created numerous records that showcased the aircraft's exceptional capabilities. The Concorde's engineering excellence manifested in numerous groundbreaking achievements. The aircraft maintained a maximum cruising speed of Mach 2.04 at altitudes up to 60,000 feet. This exceptional performance enabled the Concorde to set multiple records, including: in February 1996, it completed the transatlantic journey from London to New York in an astonishing 2 hours, 52 minutes, and 59 seconds. In November 2003, the aircraft recorded an impressive flight time of 3 hours, 55 minutes, and 12 seconds while traversing the United States from east to west, reaching a ground speed of 1,488 miles per hour in December 1985, reaching a maximum altitude of 68,000 feet during a flight in June 1973. The Concorde's relentless pursuit of supersonic speed brought with it substantial fuel consumption demands, reflecting the aircraft's unique operational profile. During the taxi phase alone, the Concorde consumed approximately 2 tons of fuel, underscoring the energy required even before takeoff. The transition to flight and the dramatic acceleration necessary to break through the sound barrier were particularly demanding, requiring fuel consumption at a staggering rate of 32.5 liters per second. Once cruising at Mach 2, the Concorde exhibited an average fuel consumption of 25,629 liters per hour, a figure that highlighted the immense energy needed to sustain supersonic speeds. Remarkably, half of the total fuel load was expended during the critical phases from takeoff to reaching its peak cruising speed of Mach 2.02. Compared to conventional aircraft, the Concorde's fuel efficiency presented notable contrasts. Its consumption rate was approximately 4 times that of the Boeing 747 on comparable routes. Modern aircraft comparisons show even starker differences, with the Concorde using 20,500 kilograms per hour compared to the 787-9's 5,400 kilograms per hour. The Concorde's operating capabilities were defined by specific parameters that balance performance with practical limitations. The aircraft achieved a maximum range of 4,090 miles with maximum fuel and reserves, though this varied based on operating conditions. At Mach 0.95 subsonic cruise, the range with maximum payload reached 3,180 miles. The aircraft's operational envelope was constrained by several factors such as maximum operating altitude 60,000 feet, landing speed requirement 162 knots, rate of climb at sea level 5,000 feet per minute, maximum permissible range 4,500 miles. These performance metrics reflected the engineering compromises necessary for supersonic commercial flight. The aircraft's thermal management systems had to contend with external temperatures ranging from -45 to 70 OC at cruise altitudes, while the airframe itself experienced temperatures up to 127 OC on the nose and 100 OC on the wing. The combination of these capabilities and limitations shaped the Concorde's operational profile. While its speed records demonstrated unprecedented achievement in commercial aviation, the fuel consumption rates ultimately influenced its economic viability. British Airways faced yearly operating costs of approximately £1 billion due to these performance characteristics, equivalent to £1.75 billion, equivalent to $2.20 billion in modern terms. Safety engineering features. Safety engineering formed the backbone of the Concorde's design philosophy, incorporating multiple layers of protection and redundancy to ensure reliable operation at supersonic speeds. The Concorde's safety architecture centered around multiple redundant systems, particularly in critical areas. The aircraft featured a sophisticated hydraulic system operating at 28 MPa, enabling lighter components while maintaining reliability. However, early testing revealed potential vulnerabilities in the hydraulic system's isolation between components. To mitigate these concerns, engineers introduced multiple independent hydraulic circuits to ensure continued functionality even in the event of a failure in one system. Backup power systems were added to support critical components, while redundant flight control mechanisms and dual autopilot systems provided additional layers of safety and operational integrity. These measures collectively enhanced the aircraft's resilience and ability to operate reliably under a variety of conditions. The Concorde's emergency systems underwent rigorous testing and continuous improvement throughout its service life. Following the 1979 Dulles incident, a series of critical safety enhancements were implemented. These included the installation of tire under-inflation pressure detection systems to preemptively identify potential failures, the reinforcement of structural capabilities in the main landing gear tires and wheels, and the integration of improved monitoring systems for critical components. The aircraft's emergency protocols included comprehensive battery management systems that monitored and controlled battery performance under all foreseeable conditions. These systems were integrated into the aircraft's software and electronics architecture to ensure safe operation during both normal and emergencies. The Concorde underwent what is widely regarded as the most comprehensive fatigue testing program in the history of aviation, designed to ensure the aircraft's safety and durability over its operational lifespan. This rigorous testing regime involved multiple specialized assessments. Static testing evaluated the airframe's structural integrity, with over 5,000 hours dedicated to analyzing its ability to withstand the stresses of flight. Acoustic fatigue testing focused on the resistance of critical components like the tail and fin to the intense noise and vibrations generated during high-speed operation, totaling more than 2,000 hours. Additionally, temperature cycling tests subjected the airframe to over 3,000 hours of thermal stress evaluation, simulating the extreme heat variations encountered during supersonic flight. Engineers conducted detailed analyses of the Concorde's airframe to understand its response to the repeated loadings of regular flight cycles, the dramatic temperature changes from supersonic operation, and the acoustic stresses inherent to sustained high-speed flight. These tests also assessed structural fatigue over prolonged use, ensuring the aircraft could maintain its performance and safety across decades of operation. The aircraft's structural design incorporated advanced aluminum construction using a specialized high-temperature alloy similar to that used in aero engine pistons. This material selection provided optimal weight characteristics while allowing conventional manufacturing techniques. Following the tragic accident in Paris in 2000, the Concorde underwent a comprehensive review to enhance its safety further. The investigation involved an exhaustive process that included on-site analysis of the wreckage, evaluation of systems and engines, in-depth review of flight recorder data, performance assessments, and comparisons with prior incidents. Multiple working groups collaborated with international aviation authorities and manufacturers to develop and implement new safety measures. The improvements introduced as a result of this investigation were significant. Enhanced tire protection systems were designed to minimize the risk of debris damage. Fuel tank linings were strengthened to reduce the likelihood of punctures in the event of an incident. Maintenance procedures were modified to incorporate lessons learned from the investigation, and emergency response protocols were updated to reflect the latest safety standards. The combination of these safety features and continuous improvements contributed to the Concorde's remarkable safety record throughout its operational life. Despite operating at twice the speed of sound, the aircraft maintained an impressive safety profile through its sophisticated engineering solutions and rigorous maintenance protocols. Environmental impact assessment. The environmental footprint of supersonic flight presented unique challenges that influenced the Concorde's operational history and ultimate retirement. Detailed studies conducted throughout its service life revealed significant impacts across multiple environmental dimensions. The Concorde's pursuit of speed demanded extraordinary fuel consumption rates that far exceeded conventional aircraft. During cruise operations, the aircraft consumed 25,629 liters of fuel per hour, a rate that translated to significant operational costs and environmental impact. Comparative analysis of modern aircraft revealed striking differences. The Concorde's fuel consumption was 20,500 kilograms per hour, while more efficient aircraft like the Boeing 787-9 consumed just 5,400 kilograms per hour. The Airbus A350-900 used 5,800 kilograms per hour, and even the larger Airbus A380, with its greater capacity, burned 12,000 kilograms per hour. The fuel system's complexity extended beyond mere consumption. Engineers designed specialized systems to prevent fuel boiling at high altitudes and manage thermal stability issues. The fuel acted as a critical heat sink for various aircraft systems, requiring careful temperature management to prevent gum deposits in pipes and heat exchangers. The Concorde's pursuit of speed resulted in fuel consumption rates far higher than those of conventional aircraft, leading to substantial operational costs and significant environmental impacts. During cruise operations, the aircraft consumed 25,629 liters of fuel per hour, a rate that dwarfed the consumption of modern aircraft. For comparison, the Concorde's fuel consumption was 20,500 kilograms per hour, while more efficient aircraft like the Boeing 787-9 consumed just 5,400 kilograms per hour. The Airbus A350-900 used 5,800 kilograms per hour, and even the larger Airbus A380, with its greater capacity, burned 12,000 kilograms per hour. The fuel system was designed not only to handle these large quantities but also to address the unique challenges posed by supersonic flight. Engineers incorporated specialized systems to prevent fuel from boiling at high altitudes and to manage thermal stability, as the aircraft's high-speed operation created extreme temperature variations. The fuel also played a critical role as a heat sink for various aircraft systems, absorbing excess heat and maintaining system functionality. This required meticulous temperature management to prevent issues such as gum deposits in pipes and heat exchangers, which could impair performance. The Concorde's operations also attracted significant scrutiny due to its environmental impact, particularly noise pollution. The Federal Aviation Administration, FAA, monitored noise levels and found that the Concorde's noise during both takeoff and landing exceeded that of conventional aircraft. Community response studies revealed considerable public concern, particularly in areas near airports where the aircraft's operations generated substantial noise. Detailed analysis was conducted on the building vibration effects caused by the aircraft, and special monitoring stations were established around airports to assess the full extent of the impact. The aircraft's supersonic speed also resulted in a distinctive sonic boom, which contributed to additional challenges. Beyond noise, the environmental effects of supersonic flight extended into the atmosphere, where scientific studies identified multiple detrimental impacts. The Concorde's high-altitude operations contributed to stratospheric issues, including the catalytic destruction of ozone by nitrogen oxide emissions. Water vapor emissions from the aircraft further exacerbated ozone depletion, while sulfate and black carbon aerosols increased surface area density, facilitating heterogeneous chemistry that could lead to further environmental harm. The projected impact of widespread supersonic aircraft fleets was substantial, with fuel burn estimated at 122.32 teragrams per year, NOx emissions contributing 1.78 teragrams of nitrogen dioxide per year, and water vapor emissions reaching 151.31 teragrams of H2O annually. Perspective: these emissions contributed to complex atmospheric chemistry changes. The water vapor released in the stratosphere acted as a greenhouse gas, warming the surface while cooling the stratosphere. Sulfate particles and black carbon intercepted solar radiation, leading to surface cooling while warming the stratosphere. Recent studies have demonstrated that supersonic aircraft continue to have a greater environmental impact than their subsonic counterparts on both per aircraft and per passenger basis. The emissions at higher cruise altitudes resulted in increased atmospheric residence times, intensifying some atmospheric responses. The International Civil Aviation Organization Committee on Aviation Environmental Protection recognized these challenges, particularly as they considered certification requirements for future supersonic aircraft. The environmental impact assessment highlighted the need for careful consideration of fuel composition, with studies showing that zero-sulfur fuel could reduce ozone depletion by 52%, but would increase net climate forcing effects. These environmental considerations, particularly the high fuel consumption and atmospheric impacts, contributed significantly to the operational challenges faced by the Concorde. The aircraft's environmental footprint became increasingly important as global awareness of aviation's climate impact grew, influencing discussions about the future of supersonic commercial flight. The Concorde is a remarkable example of human ingenuity and engineering, pushing the limits of technology with its groundbreaking design and systems. For nearly 3 decades, British Airways and Air France safely operated this iconic aircraft, setting speed records while ensuring passenger comfort at 60,000 feet. Its complex maintenance requirements and high operational costs led to its retirement in 2003, but its influence still shapes modern aviation. The Concorde pioneered technologies like fly-by-wire controls and advanced thermal management, setting the stage for future innovations. As we look to the future of supersonic travel, do you think what lessons from the Concorde can help create a more sustainable and efficient aircraft? Share your thoughts in the comments. Thanks for watching.